RealTuners Radio.
And welcome to RealTuners Radio, episode 27. It's December 20th, 2017, and tonight we have two new guests. The first is cylinder head expert Chad Speier from Speier Racing Heads, and the other is Caleb Newman from Performance Design. Get your questions ready about cylinder heads and intake manifolds, as these are a couple of our favorite go-to guys on the topics. We have our usual panel of hosts tonight as well, ready to take questions on Facebook, Mixlr, and now the RealTuners YouTube channel, all streaming live. Are you interested in taking a live in-person class with RealTuners? We teach EFI tuning classes all over the country and have opened up dates for early 2018 on our website for reservations. Classes are limited in size, so everyone gets all the attention they need. Cost is $550 for a 2-day course with live tuning of a high-performance street or track car. Our goal is to have you tuning your own project confidently and safely. We are adding classes for the year every day, so follow RealTuners LLC on Facebook or watch the schedule on our website at realtuners.com. Currently scheduled classes are as follows. January 20th and 21st, KP Racing in Houston, Texas. February 3rd and 4th, Trick Pro Motorsports in Melbourne, Florida. April 7th and 8th, we're giving our first factory ECU tuning class at Shore Tuning just outside Lexington, Kentucky. This class will cover Gen 3 and Gen 4 General Motors V8 ECU tuning. April 28th at Shore Tuning, we'll be doing our normal EFI Essentials class. May 12th and 13th, we'll be in Detroit, Michigan at Full Throttle Speed. May 26th and 27th, we'll be in Milwaukee, Wisconsin at Endless Performance. Remember, check back often. We'll announce the schedules weekly on the RealTuners Radio podcast, but we also update our website, realtuners.com, daily, or follow RealTuners LLC on Facebook to keep up on our latest schedules. These classes tend to fill up fast, so we recommend you reserve your seat as soon as possible. All right. Good evening. What's going on? December 20th. Almost Christmas. How's everybody doing tonight? So we have a whole panel of guests and a couple of special ones. We got 3 new guys on sitting in tonight going to help us out. We thought after going through all the fabrication and chassis stuff the last couple of weeks, we might bring these guys in and talk about different stuff, airflow through the engine, because we were putting our engine builder guys to sleep for the last couple of weeks. So thought we would bring in some guys that many of us have worked with in the industry who have done solid work. So I guess let's start off first with Chad Speier, man. Speier Racing Heads. Welcome aboard, dude. Can you hear us okay?
I can hear you. Can you hear me?
Yeah, we hear you clear. That's awesome.
Great.
Okay. I'm playing your slideshow now so people can see your handiwork. Cool. So Chad is a cylinder head guru, right? He's the guy you go to when you know most of your customers, it looks like, are drag racers. And I mean, it seems like most of these guys have a goal or a target in mind. So they come to you to try and figure out, okay, I got a certain range of parameters I got to be in. I got to make this much horsepower. Help me figure it out. I got to run these RPM, whatever. So Chad helps them figure out the cylinder heads. He'll specify CNC port jobs. Do a lot of really nice hand finishing. Take a look at some of the pictures that are flying by on the video right now. But anyway, so my personal experience with Chad and Mark Dahlquist on an Engine Masters Challenge 2 years project, where both years out of 50 entrants, we got a Pontiac, a crappy Pontiac, the horrible exhaust port. We got that in 9th place both years, that's actually pretty outstanding for the budget and the technology that we were using. So anyway, welcome aboard, dude. What's new? What are you working on these days?
Well, I'm actually just trying to expand the line. I think it's time a little bit. I mean, I've kind of slowly been working into the LS stuff. I don't know. I'm kind of an old school guy, grew up around comp eliminator and small blocks have always kind of just been what I've been into. And, the 23 degree deal, everybody keeps telling me that it's a dying deal. And I keep reminding them that it's alive and well. We got a think outside of just drag racing. You know, I mean, just about every Saturday night local track out there has got a 23-degree late model engine.
Right.
So, but I
super
started to see a lot
popular
more
stuff.
LS stuff.
Yeah.
Yeah, I mean, and you know what, the 23-degree stuff. I mean, I've got some engine builders now building 440s. We're with a low port 23-degree knocking on 900 horsepower now. I mean, it's just crazy. You know, it's just absolutely
nuts.
crazy.
That's nuts.
You know, I can remember probably like 5 years ago, you know, I was, you know, really looking at the 23-degree deal, wondering what I needed to do to a core, what I need somebody to do to the core to make it even possible. And at that time, Darren was a profiler, and I asked him, he goes, why would you want to do that?
You're talking about Darren Morgan, right? Another cylinder head guru.
Goes, why would you want to do that? And I'm like, well, because no one else is doing it. He goes, that's just stupid. It's not stupid, man. He goes, you could do it so much easier with an 18-degree. And I'm like, 18 degrees a dead duck.
Yeah.
You know, and that's what I see now. I mean, now it's 23-degree LS, and everything else just gets jumped right over, and then it goes to the spread port, or, you know, some of the weird stuff that really flow a lot of air. Now, I mean, you got some small block cylinder heads that are actually go on a 23-degree block or a standard block that flow more than a big block head. I mean, it's just
right.
It's just crazy.
Nuts.
Absolutely crazy.
Yeah.
Well, and some of the super late model 12-degree symmetrical port canted valve stuff is way out there too. No,
it's insane. I mean, that, you know, I just was working on a set of those today, a set of that, you know, the 12-degree profiler deal, and it's a 2230 or 2240 valve, and I mean, it's knocking on 490. I mean, it's just crazy with a 4200 bore, you know. And I mean, the ports are huge, you know, and I think that's a lot of the internet stuff too. You know, people start talking about CC wise, and they look at a small block port that's 420 cc's, and you know what, it needs to be that big to be proper, you know, because they're moving a ton of air nowadays, you know. But it's crazy. I mean, I look at some of this stuff and I go, are you kidding me?
Yeah.
You know, I'm the one standing there doing it. I'm like, are you kidding me? It's just crazy to me.
So but let's talk a little bit about port size, because you're not so much as of a CC guy, because CC is length and width and height versus area, which is strictly a cross sectional area. Do you want to expound on how you develop a port with area and velocity?
Well, I mean, I think it's obviously everything's a ratio of the valve, you know, so that's the first thing you got to depend. And then it depends on what geometry you're working on. You know, I mean, I still am a firm believer that the minimum needs to be the seat ring, you know, but then you get some of the theories are that a larger valve, put the largest valve in the bore you can. And, you know, at the end of the day, that makes a really big port, especially if you want the minimum at the seat ring. So it all comes back down to application, you know. But to be honest with you, you know, I mean, if anybody's ever followed me around the internet, I keep preaching formulas, and I'm telling you right now, man, I live by them. I use it in a head that you're familiar with 100%, that Pontiac Engine Master head. It's the same way. You take any of those formulas, you take what it flows times 2.4 divided by 350 feet per second, and it's 2.66. And what's the cross section at the pinch, Mark? 2.66. Wow. So, you know, I think a lot of times people get the information, and there's people out there talking, and they don't ever think that they're giving the right answer because they're not going to give it away. And I don't do that. I mean,
that's why you're on here. We were like, oh, Chad doesn't really ever hide anything. He doesn't act like he knows everything either. So, I mean, yeah.
Yeah, no. And, you know, and that's the thing. And I get jumped about that all the time. And, you know, I can say, okay, Mark, you need to give that head a 91.5% throat. Okay. And then the next day he says, okay, I give it a 91% throat. And I'm like, okay, let me show you giving it a 91% throat. And then after that's accomplished, then it's him actually doing it. So there's really three sizes. I can tell somebody all day long what to do or what size to make it, but until you physically put hand to grinder and stone or whatever to the port, it's just a number, right? You know, and it's you don't know anything till you've done it.
And you're validating a lot of this stuff with track performance too, right? I mean, you.
Oh yeah, absolutely, yeah.
Because I mean, I follow a lot of your customers are always going back and forth with you on different posts or Facebook groups or whatever, and talking about, okay, we've got this result, we changed this is what we did, and it's like they just do that over and over, and they develop their program.
I don't have a dyno, and I was told early on, if you want to be successful, you got to have a dyno, or you got to have somebody that's willing to help you, and I've went to chassis dynos and, taken LS stuff or whatnot and changed it right there and put it back on. That's what it's all about.
Yeah.
And I there's a lot of debate on the perfect port shape, and I don't really think I don't know how you're ever going to know that. I don't know if a CFD can do it.
Right.
I don't know if the track's going to tell you it's 20 runs down it. I definitely don't think a flow bench is going to tell you. But I think if you understand all that stuff, you've got a better than average shot of accomplishing it. And then you need feedback. And then after you start getting your feedback, you need a data log. And then you start looking at it, and early on especially with the 23-degree line, dudes, I ship stuff to people that I change something up every freaking time because that was the only way I was going to learn.
Sure.
I'm like, this cylinder head's going to get a 40 wide seat with a 60 that's 100 wide, and this cylinder head is going to get the same seat, but it's going to get a 40 wide 60. Other than the high end guys, something like what Mark did with all the dyno pulls and whatnot. Let's face it, the average DIY guy or bracket guy, they're going to put it together in their garage. They're going to go.
It might get one trip to the dyno if it's really lucky.
Right.
Yeah.
And the guys that actually have, and Chris Cobb's helped me a lot along the way. This guy's got probably 10 of my manifolds. He's probably got even when he dynos stuff that doesn't have my cylinder heads on it, he'll put my manifolds on it. He'll call me.
Yeah.
Hey, this manifold did this manifold did that. So, over the years, I've got a really good baseline. I can, I feel like and that's the thing is everybody, they'll paint that broad question, what manifold needs to go on a 427?
That drives me nuts. Oh, the LS world is suffering from that big time.
Yeah. I can't tell you what with a Brodex head or with an AFR, but I can tell you with mine, but I should know that it's my business. You know what I'm saying? But it takes a lot of, I've sent a lot of stuff off that I didn't charge anybody. It's just what you have to do, and I believe that a small business has more time than money, and
Sure.
sometimes your labor is the cheapest thing you have.
Yeah, but let's be honest, in a consistent car and the track incrementals are as helpful as a dyno.
Oh, absolutely.
That's what you're trying to do anyway. You're looking
exactly
for
right. The track's
performance
not
and
going to lie to
consistency.
you.
Yeah.
Yeah, the track's not going to lie, and then along the way, and then I have all that stuff, and then I have my comp guys, which, in my world, I'm an NA guy. I bleed NA, and I've seen some stuff that just make your head spin, and those guys teach you a lot, and this my super stock guys. If you want to learn all about velocity and learn about what a 165 or 172 cc port will do, you need to port a super stock head, because at the end of the day, when you're done, you're going to go, there's no way. And they're going to go, well, there is a way. I just did it. Those engines are incredible. They're most of them are 350, 300 horsers, and they're making 625, 630 out of a 194 head that flows 260 on a good day. So flow numbers aren't everything, just peak flow numbers. Not. Yeah. No, absolutely not. They got stupid, crazy fast velocities through the pinch, and it's just, and I think too, I truly believe in velocity. I'm more about velocity than anything. And, I can remember standing in front of a flow bench in the midnight. In fact, I posted it on Facebook one day. I still had the very first cylinder head I ever ported. I still have the velocity report for. It's interesting. No, yeah. I remember when we were narrowing down the cross-sectional area of certain parts of the port, like on that Pontiac, playing with it and picking up torque, because of the velocity, and it was helping the point score because it was getting us stuff more down low, and that was a nice big power curve. I don't have a picture of that, but I'm putting up all your other website pics right now. So yeah, I remember that Pontiac was a weird deal, because that was a cylinder head that if you sitting here and somebody asked me, what about putting a 2.350 valve in a cylinder head that's got, not even a little over 2.5 inches at the push rod? I'd be like, there is no way on God's green earth it's going to work. But you know what? It worked. But I truly believe that you've got to set the port up for it. And, Mark can vouch, the back half of that port is stupid big. that port ended up, I don't remember how many cc's, but it was a ton. I didn't pour it. I didn't want to, but I bet it was 330, maybe bigger. Yeah, it was huge. But there again, okay, so what was the RPM at that time, Mark? 6,500, 7,000?
Yeah, first year was 7,000, and then the second year was 65.
Okay, so we got a 428 cubic inch engine that's got a 330 cc port on it. Same thing what we did with Henderson's a few years later with the 406 that had a 290 cc 13 degree port on it. So I guess my point is if the port is balanced, it's, people keep saying, I keep reading it over and over and over, that airflow doesn't mean anything. No, yes, guys, it does.
It does mean
because
something.
If it's not, if it's not moving enough air for that port, then that port's the lazy pig, and it's all dependent on how much air it's moving. So
we've actually got a listener here. As long as you're talking about your flow bench, he says he's never used a flow bench, but he's heard that if a port is quiet on the flow bench, it will work better. Is there any truth to that?
You don't know how many ports I've turned off the electronics and just flowed it.
Just to hear it?
Just to hear
I've heard one other guy that Ray Barton said that to me once. He's like, yeah, and you turn it the other way and listen it to the other direction. And he wanted it to squeal one way and sound smooth the other, or some shit. I'm paraphrasing. I don't remember the whole thing.
In fact, I have a beta deal from Performance Trends that requires a microphone that records audio clips of a port being flowed, and then it creates its database, and then you pick the port that sound the best, that ran the best, and then it compares everything to that, and it gives you a percentage of how efficient or inefficient it is compared to your
baseline recording.
Yeah.
Wow, that's kind of neat. That's kind of cool.
Kind of neat. And it basically, all a flow bench is for is a visual aid. I keep always saying it's the lifeblood for a flow bench, because I without my pitot tube, I'd be lost, and I've, over the years I've caught a lot of grief, and I keep saying, well, it's because you don't understand it.
You use the pitot tube to measure instantaneous velocity at any given
localized velocity. Yeah.
Got it. Okay.
Yeah. Absolutely. Wow. And then all you're really after is a gradient. You want it tight, top to bottom, and you want it balanced. I mean, for instance, like the 13 degree profiler CNC port, I can put the pitot tube right in the middle and start at the beginning and finish as far back as I can get it. And that velocity doesn't change 15 feet per second.
Wow. Okay. That's interesting.
So
do you have any kind of a way that you determine, what kind of base velocities you're getting out of something, like without, like for the little guy who's just out there looking at heads on the internet trying to buy, do you have something when the guy looks at it and goes, oh, it says these flow numbers, but I'm not caring about those because I know that potentially I need enough flow to make that velocity happen. So do you have like a base math formula that you go by? That
300 at the minimum. So let's say, that's all going to be dependent on the company advertising minimum. So let's say you have a port that flows 290 CFM. You can do your math and you can find out what the velocity is through the minimum, which on a 23 degree, obviously, it's going to be the pinch or the push rod area. They don't like calling it the pinch, but anyway. But yeah, a lot of my stuff is based off of 300 to 310 through the minimum. And I've kind of narrowed it down over the years to where a small block Chevy is going to flow 125 CFM per valve diameter. So those are the little things you pick up on.
So you're taking the overall the flow numbers and figuring out based on the valve diameter the ratio at that point.
Exactly. So let's say like we'll just pick on a 23 degree. Let's say we've got a 208 valve. I'm gonna want about a 91% throat. You're gonna get about 125% at the area at the push rod, and then it's all balanced from there. So you could, but see, now this will catch you because there's a lot of guys that don't believe, and if you look at anything that I do that's got a big bowl in it, man, I'm talking 100% valve. I mean, I got a small block head that's got about a 240 bowl in it. It's huge. That 265 port, it's huge. But I truly believe that you're going to have to slow the air down somewhere. I just soon do it on the short side. A lot of guys like big throats. I mean, you'll look at some of the heads out there, like some of the Brodex stuff, the Headhunter stuff. They got 93.5% throats. They're huge. That's what have to slow the air down. You don't slow that air down, how are you going to fill it? You're just going to need more time, you know?
Well,
So everything's basically ratio.
Yeah, we just did that big block this summer where we started out with a small Brodex, and I had you open the bowls up on it.
Right.
To even on that big block, and it made just crazy amounts of torque for a low compression pump gas deal.
Let's bring in our other two guys here. Just real quick, because I mean we're sitting here talking airflow, and they're probably like, "Shut up, you fool!" No, it's all right. I don't know. They may have just been like, "These guys are dumb. We're leaving." But,
yeah.
No,
and this same person also helped with that same weird archaic Pontiac.
Correct. So let me just go ahead and introduce from Performance Design, Mr. Caleb Newman, and also he's got his coworker Joe is with us tonight here. Do you guys, I don't know, are you still at work or where are you guys at?
We're outside of Detroit. We're in Auburn Hills.
Okay.
So that's a funny question because we're kind of working now, right? But we love this stuff, and I had to actually mute my microphone because there are a couple times I was chuckling. There's so much what Chad is saying that's the same for us that really we kind of drive based on some kind of analysis at the beginning, but then after that, there's a certain point in which I don't really care about certain things like flow bench. I get the question all the time, like, well, what's that intake flow on the flow bench? Mm-hmm. I ask, well, why do you want to know? We don't generally flow intakes. Now, I should qualify that statement. We do CFD, which is effectively a flow bench, but there's different levels of CFD, and we start off with one that's we generally use more for qualitative than quantitative flow. We'll look at relative numbers, but it's only an indicator, kind of like a flow bench. The numbers are not linear to performance. It's not a linear relation. It's not, you can't always correlate the flow data to what it does on the dyno. I'm a fan of the dyno, but you know, the racetrack is kind of the same thing, right?
Sure.
It's absorbing
Caleb,
power.
Can I interrupt you for a second?
Yeah, I wanted Mark to give a little bit of background info first before Caleb got too far into it. So just so that people know just who we're talking to here.
When Caleb says he likes to validate on the racetrack, some of his intake manifolds, I think when I first talked to you, had worked for a number of years for K-Tech before you went full-time on your own at Performance Design, but I believe the C5R and C6R and maybe the C7R are all year.
The manifolds? Corvette road racing programs, like the Le Mans cars, is that correct? Or where did those cars race?
Yeah, Le Mans, Daytona 24-hour. So those are not mine per se. K-Tech did do the C5R, and we did several different iterations, and I was part of the team that helped that happen. At that point, I was more on the manufacturing side. But we did several iterations of the C5R. The C6R actually was done within GM Racing, but we did help on quite a bit of that, did a little bit of the development. I did several intake manifolds at K-Tech, was at K-Tech 9 years. Left there as vice president and director of aftermarket operations, but got to do a little bit of everything. A small company, got to wear a lot of hats, ran the CNC department, a lot of program management, did the V16 for GM in 2002. It was unveiled in 2003 in the Cadillac 16 concept car. My wife called that the other woman because I spent so much time with it during that project. It was so intense. Did a lot of pre-production development for LS7, the LS9. You're just getting that joke.
No, I did. It was funny. I was laughing in the background, and I think the mic unmuted itself. But yeah.
We did a lot of pre-production development for the supercharged engines, LS9, the LSA, LS7, and then we did quite a bit of race program. Obviously, did the Corvette program until GM brought the engines in-house. We did the Cadillac, the original CTSV that raced in World Challenge. I was the program manager on that as well. And that was really an awesome program because it's the closest I've seen personally where a true connection between production and racing. We were literally on the phone daily, emailing, sending data back and forth and parts back and forth with the production guys, with GM Powertrain. Talking with Jim Hicks, he was sending us valves. We tried some really trick valves that failed within like minutes on the dyno. Lightest valves I've ever seen, but they didn't work. It really was a great challenge and a great fun project where we got to work on the engine development for racing, for production, and vice versa. Like simultaneously, we're taking LS7 components and running it in a 5.7 liter race engine to 8,200 RPM. That's where those I can't remember what they call it now, but the ceramic check ball lifters that GM sells. That's where that originated from, that program when we were
the CTS VRs.
Yeah.
Yeah.
Is that a limited travel lifter? Is that what he's talking about, Mark?
No, it's the same lifter that I've got in my 6 liter. It's just it's a tricked out, basically LS7, but the tighter tolerances.
It's a ceramic check ball. Yeah.
Yep.
It's a ceramic check ball. So the mass of the check ball was really the key. When you're running up at up over 8,000 RPM, the mass and momentum of the check ball would actually keep it open, and you'd start to collapse the lifter. So, I mean, it's very simple physics, but it's the type of thing that was actually a gentleman, Kevin Lachansky at GM, I believe, came up with that idea. But we got to work on stuff like that in the Cadillac race program. And then in 2008, when the economy was just doing wonders, I left K-Tech and started Performance Design. We really started with the intent to eventually build our own products, but a lot of our history over the last 9 years has been designing products for other companies, sort of a design and engineering firm to help people develop products and bring them to market. Some examples there is the Modus V4 motorcycle engine, complete clean sheet engine, 1650cc, makes 165 horsepower in one configuration, and 185, I believe, is the rated power out of a 1650cc V4. We designed the line of intake manifolds for MSD, the Atomic Air Force. I think you guys are pretty familiar with those intakes. A lot of different projects over the years. At one point, kind of got the wild hair to start producing carbon fiber intakes, and that's sort of how we got connected with Mark. He had this really wild hair idea of doing a 180-degree tuned cross ram, which we had always kind of wanted to do after our first Carbon XR, wanted to do a 180-degree tuned version of it. After we looked at it for a little while with Mark, we kind of stopped and said, let's dial it back and go back to something simple that we know is going to work, especially Mark was under a fairly tight time frame. So we concepted a tunnel ram architecture with a forward-facing throttle, and that's where the Carbon TR came kind of into existence. That was I don't recall the exact time frame on that, Mark. What was the timing on it? We had to do that in pretty quick order, I think.
It was $3,000 worth of red label.
Yeah.
When we finally figured out how we were, or what we were going to do and how we were going to do it, I think it was maybe 8 weeks, maybe.
Yeah. I think we only had the advantage that at that point we had already tooled the top for the carbon top for a different application, but we had to design the entire bottom and tool the runners. So it was a pretty wild.
You were working on the top, I think, for your TRIC manifold, weren't you?
Correct. Yeah. And we hadn't even run one yet. At that point, we'd only tooled the top. The rest of the billet was still being done. I think your parts actually ran and made noise before the trick manifold. So It was pretty tight time frame.
We had that manifold showed up next day air at about 4:30 in the afternoon on a Friday, and we had it on the engine and running by 5 p.m. And we had the engine off the dyno at like 8 p.m. because we had to pack up and go to Engine Masters.
I remember that. We were waiting for the glue to dry on those intake stacks. That's literally what took us the whole time. We got it, opened up the box, had to do some gluing or something, and then let that dry for like a half hour or 20 minutes or something, put it on the motor, picked up 100 and some points, decided we're keeping it, and packed the motor up and left, right?
It was more or less how it went.
Yeah. So, going back to some of the stuff that Chad talked about, even that project, what we really start off with is we analyze the equations, and we usually start with very simple wave tuning calculations in a spreadsheet. And quite honestly, I have found that 70 to 90% of the work is just making sure you get the wave tuning right and attention to detail in the actual design. You always have to look at like what's the actual application, what are the operating requirements, what's the power band, and you got to really pick and choose and make sure you understand that. But once you get into the wave tuning and start packaging and paying attention to the details, depending on the application, you can get 98% of the way there, and the CFD and the advanced analysis, it only helps you get that last 2%. But
when you do CFD, when you do the modeling, sorry to interrupt, but are you trying to model pulsations from intake valve events and different pressure waves or pressure tuning, or how far do you take that?
It depends on the program, depends on the time, the budget, the level of optimization. Where do we need to hit for, what are the requirements of the program? If we've got a really tall order power requirement that we have to optimize to a very high level, and the budget allows, the time allows, we go pretty far. Start off with the wave tuning and basically start kind of concepting. The packaging drives a lot of what you can do, how long a runner you can get. So you start concepting ideas to get runner length and what you can physically package, and you iterate that with the wave tuning. From there, you need a model to do CFD. So you've got to actually physically draw this thing up in CAD to be able to run CFD. So the first step of CFD is steady state CFD, which is, I wish I'd sent you some slides of kind of the comparison, steady state versus dynamic. Steady state CFD, when I said we look at predominantly like qualitative, we will look at the quantitative values, but we generally use them only as indicators. They're not necessarily absolute truth. If we're looking at small relative changes, we can look kind of like the track or the flow bench. We can use those quantitative numbers for relative numbers, but we are really looking at the flow development. We're looking first architecturally, can we get air from the throttle to the bell mouth? Are we restricting anything? Is there tight spots in the manifold because of packaging?
And is that the goal, as least restriction as possible with even distribution? Is that the theme here overall?
It's the general goal, but there's some tight packaging constraints where you can actually take advantage of like the plenum proximity to a runner to change the effective length of the runner. But we want to make sure we can get air can we flow enough air to the bell mouth? And then it's actual flow development at the bell mouth. To me, that's one of the most critical. I think Chad was kind of talking about where he wants the pinch point. I look most at the flow development into the runner. And then once we're into the runner, we're looking for kind of velocity gradients. We're looking at how are we accelerating. We generally don't see the same velocity over the whole runner because we're taking it from a very low velocity at the entrance. So we see a lot of the acceleration before it gets into the head port, and we really want to make sure that acceleration is ideally constant, and make sure that we're not slowing down, speeding up throughout the port. If we're slowing down and speeding up, we have flow losses. There's energy loss, of the flow in the port or in the runner itself at that point. So we're looking at the gradient and how it's accelerating more qualitatively. You know, that's where the beauty of CFD, you can look at a picture and see very quickly, did I mess up my runner? And sometimes it's not did I mess up, but I'm cramped so tight into some packaging. A good example is the LS3 intake manifold. Everyone knows it's really hard to beat a production intake manifold.
Right.
When you start hemming it in to the total packaging height that we have available under hood, you start limiting your options. And when you start trying to get creative to try to fit a different tuned length or something to that effect, there may be something that you don't see in the CAD. You know, as soon as you see it in CFD, you go, oh yeah, I see it now. So we use that. That's kind of step one for CFD, steady state. The next is we will look at dynamic CFD, where we'll actually flow with, generally you simulate it with a pressure pulse at the valve that we either know from the engine or we can estimate it fairly closely what the pressure at the valve looks like. And we'll run it through the actual firing order, and you can see the flow, the dynamic flow over the firing order. That's kind of step two. The step beyond that is to simulate that with compressible flow, where you actually see the compression wave in the flow. You see the inertia of the air. That takes 10 to 25 times the computing power that the step two does, and that's more like production programs. It's more bigger performance
large scale
programs
projects.
Large scale that really has, it's a lot more budget. It can literally take 1 to 2 weeks just to run that simulation on a fairly robust computer.
Right, and you have to rent time on that fairly robust computer that costs a lot of money, and yeah, that's supercomputer type of analysis. But we do it. That's why I was saying I wish there's actually some videos that we have where you can see the wave. You can visually see the wave and the airflow compressing and then bouncing back out to the bell mouth and dispersing into the plenum. So not to interrupt, but what we can do is you can send me those afterwards, because there's only a couple hundred people listening tonight, but there will be 800 listening, downloading the podcast tomorrow. I can put on the video. I can load that up after the fact. So I'll get with you after this.
I'll have to make sure that we can release
anything you can share by all means, but don't get yourself legal. Don't get any lawyer letters sent at you.
Yeah. Well, so the big part of a lot of what we do, a lot of it is confidential, so we can't talk about everything, but the concepts are kind of the same across everything. The last step of the analysis that we do, and we actually do fairly often now, it's something that is fairly unique. We just recently merged with MPI. MPI manufactures all the plastic intake manifolds in the performance market. They're a manufacturer. They can help develop, but that's where our strengths are, and that's where we found a very good overlap of our skill sets to work together. They have this development, simulation technique where they actually look at 3D acoustic analysis. What we're looking at on a spreadsheet is basically 1D wave tuning. We're looking at a length. How long does it take for air to the sound, the speed of sound in air at different operating conditions to travel back and forth. The 3D is actually looking at the 3D geometry and looking at how the geometry turns, curves, taper in the runner, how close it is to the plenum wall, what resonant frequencies are there inside of that runner that will affect how it tunes. What we've found is the dynamic CFD and this acoustic tuning analysis really, really closely approximates what we see on the dyno. It hits, you can look at air-fuel distribution or total mass flow of air into each cylinder, and that simulation will generally match the trend on an engine that we see on a dyno with real data when it's instrumented, versus a steady state CFD will not show you the mass flow difference. that's why you can't look at it as an absolute number. When you combine these two, you start to understand the little changes that we make in the design. We can see how it's affecting the acoustic resonance, a 3D acoustic resonance in the runner. And that's really, really powerful. That is surprisingly fairly efficient process to run. So we generally run the first either steady state or the first step of dynamic CFD. A lot of our performance intake manifolds, though, we generally use that first step, wave tuning and very fine attention to detail. There's a lot of empirical expertise that goes into stuff like the TR. I don't believe we even did CFD on that manifold, but obviously, Mark, you saw it worked really well for you, right?
No, it was great. And I mean, for you guys, it was just kind of winging it. They're not winging it, but like, okay, well, we know based on this, a bore stroke, whatever. And you guys worked with Chad, and it was something you were able to closely approximate. And it would, right off the bat, the low RPM to high RPM, it made more horsepower than and tuned more easily, had better distribution per cylinder than what we had been using previously, which we knew was a bit of a compromise.
But you told us to look at the torque curve, and we would see. You told us where we were going to see the peaks and the valleys all the way through, and I think there was one you were off maybe 50 RPM.
Yeah, it was pretty ridiculous.
Yeah, usually. So the first step was we analyze it and kind of look at the numbers, look at the equations, like Chad's saying. The second is flow bench. Then we start designing it. But that closed loop, getting the data back, when you get the data back from the customer, that helps immensely. And usually what we're looking at is are the tuning peaks in the torque curve. You can, once you know what you're looking for, but once you actually think about looking at the torque curve for tuning peaks, like where does it really tune in, you start to see little valleys or peaks. And when you equate that, where do those hit compared to what my analysis said it would, that tells us what the effective tuning is, because the wave tuning on a spreadsheet is just in a perfect, that's a perfect length. Yeah, so in reality, the geometry is different. Plus, we have other tuning effects, right? The exhaust, the cam, etc. That changes everything as well.
When you say wave tuning, are you talking about trying to hit a specific hertz or specific frequency, or what are you looking for exactly?
Yeah, we look at, generally we're trying to hit like anywhere between 3.5 to 5.5, fifth, sixth order, depending on the packaging, what you can fit. Sometimes it's higher, trying to hit those orders on ideal peak power or peak torque locations. If you're trying to hit, I actually pulled up the Pontiac spreadsheet, and I thought I did. I believe this is the correct one. It was a 6.5 inch length in the head port, and we had.
And Chad actually did the digitizing on the port for us. Okay,
yeah. Well, I think you gave us that, but then you gave us the digitizing, so we estimated from the CAD, and we ended up designing to a 7.8 inch runner length, and that gave us a tuning point at 4.5 order of about 6390, 6400 RPM. And we generally look at like the 80 to 85 degree temperature. It's only important that we're consistent or fairly close to what you're really going to be operating at. So I think from memory, I think you were targeting like a 6400 peak, and that was a length that gave us a nice tuning point at the 4.5 order tuning node. And then like the next one, fifth order, was almost 5800. So you get different tuning nodes. And what we were trying to do was look at your torque curve after. That was the first thing I think I asked for, was a picture of your torque curve, so we could see, did we hit it, or are there other factors going on? Sometimes you don't always hit them because there's something else that's basically canceling out that tuning.
So far, we've talked about intake runner tuning, we've got several guys that are asking, how does the plenum affect that?
Plenum volume?
Yeah.
Plenum.
So theoretically, the larger, if you go to a infinite, if you go to ITB throttle with infinite plenum, they don't affect each other. So you're tuning directly on that runner only, on its tuned wavelength. So as you start to shrink down the plenum, there's a balancing act. As you go smaller, you get faster responses. You've got less plenum to fill, but you get what I was talking about on that 3D acoustic tuning. You actually get tuning effects out of the runner to the plenum wall. And if you're really tight, it can drastically change the tuning of that individual runner. An example is when you go to a tangential feed into the plenum. So if half the runner is a bell and the other half is part of the plenum wall, that plenum wall effectively lengthens your runner, and so it tunes at a lower RPM.
That makes total sense. Yeah.
We strive to have a raised bell mouth in any application we can so that we're not affecting the tuned length of that runner with the plenum wall itself. Sometimes you can't do anything about it. When you go to like a carbureted manifold, you don't want a raised bell, so you're not puddling. There's different factors on why you would do something. But yeah, the plenum does definitely play into effect if you start getting tighter or you have things like tangential plenum walls to the runner itself.
Caleb, have you ever done any like wet flow data?
Is there a specific formula that you work off for plenum volume, or and maybe Chad, you want to chime in? You do a lot more with single plane manifolds with a common plenum. How does plenum volume affect an intake manifold?
I just basically start with the plenum starts as cubic inch of one cylinder, if that makes sense.
That's what you want as a minimum?
Yeah, that's where I would start. Yeah. And then, like a lot of the sheet metal stuff, I mean, like I did a little 4-banger deal and it was like 3 times cubic inches of the engine is what it wanted. So the engine was 200 cubic inches. It wanted 600 cubic inches of plenum. It was huge. But that thing had standoff. That's a whole new world right there.
Yeah, I find 1 to 2 times displacement for plenum volume is my general, that's kind of rule of thumb, that below that you could start to have some restriction. The other thing I was going to say in terms of the dyno feedback, I look at the tuning peaks on the torque curve itself, but we also want to look at the map. Are we restricting, do we have any sort of issues with our manifold pressure? Are we choking flow? Are we seeing anything at any specific RPM? That kind of tells us, is our plenum too small, or do we have pinch points we're not able to feed to the plenum because of the dynamic firing order, etc. So I generally start with a 1 to 2 times engine displacement. The other reason that fits well is you start getting bigger than that, and most of the time, a lot of what we design for is constrained by hoods or other packaging. So getting much beyond 2 times, it's difficult to package most of the time. Getting below 1 times displacement, I tend to see more issues where it affects the tuning, or you have worse airflow distribution.
Yeah, then you got some guys, like with some sheet metal stuff, they got all these plastic spacers and they look like they got like 4 times the plenum volume, but what they're not telling you is they got the manifold stuffed. They got some sort of stuff for directors, and they're not showing you their cards on that deal.
I got one. This is a good, decent question. How does manifold, like pressurized air in the manifold, about 20 pounds of boost, or what most of our listeners are, forced induction or power adder guys, just curious how much of that changes if we tell you that we're going to run 20 or 30 or 40 PSI of manifold pressure, of inlet pressure.
Do you want to go, Chad, or I've got some thoughts on it.
I got. I mean, My limited stuff is it just seems that, especially with the power adder for like a turbo deal. I mean, I've got, again, we're talking about, even cylinder head wise, but I've got a guy that runs X. It's got two 70s, and I got a set of 12 degrees on it, and that port's 470, and it's 400 inches, and it hauls them out. Then I do cylinder head work for a converter guy here in Kansas, which I'm not going to say his name, but he, it's Ford stuff, and they're using a Vortec. I think, is it a Vortec? Is that the blower, that little Benny deal? But anyway, and his stuff's no bigger than an NA head. So, man, I don't know. It confuses me. I'm not going to lie about it. I don't know. I would call a guy like Caleb, truthfully.
So what I generally start off with is what's good for NA is good for boost, with exception of cam overlap. And but the reality is usually there's other constraints that you have to have a shorter runner. Like if you got a supercharger sitting on top, you may not be able to fit the same runner length. So it most often, in my experience, comes down to packaging. If you can't package the same thing that you would for NA, that you go shorter, and that's the beauty of boost, is you can overcome. But if you want to optimize it perfectly, you would still try to get your tune points. Now it does change the operating, the pressure and temperatures change, so your wave tuning the speeds will change. So you have to account for that, but you would still generally kind of do, you still want to look at the wave tuning. If you can't, you can usually overcome it with boost. And I find it's usually packaging driven. The thing I find most often is you're just limited in total length that you can put into the runner. So you still look at just shorter runner lengths, but what hits tuning nodes that still are in your operating range.
So your new
I think most people are going to run into a packaging problem before they run into issues where they're really worried about the tuning of it, because so many guys are cramming something underneath the hood that they're trying to make it so they can drive it on the street nowadays. So they don't want a 6-inch cowl up there. They want,
I see what look like a lot of compromises in that department. Yeah, some of these sheet metal things are really small plenum volume, or they're really low. On all sorts of engines, big blocks, small blocks, LSs, all turbo stuff. And they're like, oh, we just turn up the boost to make up the difference. But the stuff I've seen as a tuner is those can be hard to tune off idle, hard to get them to stage on the converter, and to build boost at that lower RPM. And, they don't make much.
There's always sacrifices when you have to go smaller, but that's one of the big problems, is that people have to go smaller because they're packaging something that's not really a full out race car. It's still a street car. It's something they drive pretty often, and they're
but you see the same theme on pro mods, on turbo pro mod cars. Like somebody just doesn't really care.
And I think that's a big debate too. There's always a big debate on how much bigger the induction needs to be sized for an adder or for that. And in my personal opinion, I don't think that's the side that needs to be different. I think that all comes down to the exhaust side and the chamber and making it easier to tune.
And valve
here's a list of reasons why AT&T Prepaid is a great choice. When you switch to AT&T Prepaid, you get a new ZTE Maven 3 smartphone for free.
When you switch to AT&T Prepaid, you get a new ZTE.
That's coming from the phone. That's one of those guys. Sorry. Hold on a second.
I was going to say, Scott, did you sell out on us?
No, I don't even know what the hell that is. That's coming through the phone line. I don't know if that's coming on Caleb's line or what the deal is, but hold on a second here.
Can you hear me, Caleb?
Coverage and other restrictions apply. Details at AT&T.com.
Into the commercial right there. What was that?
No, you guys dropped out on me for a little bit.
Sorry. I had to mute you because I was getting like some radio commercial or something coming through the line. It was coming through the phone line. I don't know what that was.
So Caleb,
That's awesome. I'll edit that out. Don't worry.
Caleb, you've got a new manifold out now, the PTR, that has 3 different runner lengths in it, and I think you worked in conjunction with Fast on that. Tell us a little bit about what the 3 runner lengths, what they're tuned for, and what they do.
Well, the original concept was to do a tunnel ram style intake manifold, and it's very similar to our carbon TR, but there were a couple really key things that we wanted to look at. Number one was using plastic. Plastic is very expensive to tool, but it enables a much lower cost unit in production. And then further, it's lighter weight. It's very good for thermal mass. It doesn't heat soak like aluminum does. So it's, manufacturing wise and just performance and mass wise, it's a much better material. It's the same materials that they use in production, like all the OE. 98% of production intake manifolds now are probably plastic. That was the first thing. And as soon as we do that, it also opens up other ability to add features like the different runner lengths. You can add features that we've got a spin lock feature, so you can change the velocity stack out. So we've got a 6.5-inch runner, an 8-inch runner, and then a 9.5-inch runner. And the real key driver there is there's a lot of short runner, like sheet metal cast manifolds that are in the 6 to or even shorter, 6 to 7 inch range. They want to tune up in like the between 7,500 and like 9,000 RPM, which most guys aren't using on the street. When you do that, you also give up a ton of torque down low. You can give up in the 50, 60 foot-pounds of torque. And
this applies
sweet spot, like
naturally aspirated or boosted, right?
Yes, but I'm kind of the same as Chad. I really like naturally aspirated, so I want to make sure that works well too.
Well, you have to think about too, down where that torque is really important. The engines are typically naturally aspirated. They haven't made boost yet.
Yeah, you're not up on that boost depending on your turbo or supercharger, etc. So, so the idea was, okay, some people really do need that, right? Some people really are turning their LS engine, 9,000 RPM. Not many though. As soon as we can change that velocity stack and change the runner length, we can change the tuning to get tune at much lower peak torque, lower peak RPM for peak power. So I have found with LS engines, especially LS7 and as well as like the Cathedral port, they really like the 9.5-inch runner is a really a very well balanced runner length that gets you really good torque, really good power. You start going longer and your torque starts picking up, but you start to give up on your peak power and vice versa as you start going shorter. It's a really nice balance to me. So the real primary intent was, how can we make this tunable so we can get up to a 9.5-inch runner and give it all the features that everyone wants, right? It's got nitrous bosses. It's lightweight. It can be disassembled. You can modify it. You can grind on it. You can port on it. You can make whatever changes. We've got quite a few features underneath with heat staked inserts so that you can mount components on it. You can put all of your ports, all of your different ports and sensors down underneath the manifold that's hidden. If you're running nitrous, you can run nitrous lines inside and help support the lines. The top coming off was kind of twofold. One, we want to be able to change the runners and be able to get at everything. Two is, as you mentioned, we're working with Fast on this. We've worked with Fast for a long time. We have a very long relationship and worked really well together on things. This one we're bringing to market in a manner that they're going to bring the all plastic version. We have a carbon top version. It kind of aligns nicely with our brands, all of our carbon products that we've already got, but it also gives us a component with carbon lid and a plastic lower, gets us into like the $1,250 to $1,300 retail, which is about a third to a quarter of our next product. So our primary intent was to try to create a great performing product that's more accessible to a broader market. But the idea of having different tune lengths to me is like the no-brainer to do in plastic. It just really having those velocity stacks out of injection molded plastic makes it very cost effective to be able to change the runner lengths.
I have a question. It kind of goes back to plenum volume.
Yeah.
So is it? This may be a stupid question, but it just popped in my head. Is it necessary that the plenum volume is between the runners? Like, if you say you had a space constraint in a certain vehicle, and this is just kind of a simplified idea, but like, I mean, could you have like a section of plenum that is, say, outside of the width of where the runners are, or would that cause a problem or not work?
I'm not sure if I totally follow you, but general rule of thumb that I usually apply is ideally would be able to fit your finger in between the bell mouth and anything around it. And additional plenum volume, say, on the sides is generally advantageous. I guess, everything is kind of on a case-by-case basis, but having more plenum volume, I mean, going back to that plenum volume, usually more plenum makes more power. You start to get to a point where you may start to realize some latency in the throttle response. There may be some lag, but it's going to likely.
Chris, are you talking like a sump tank on an oil pan where it's off to the side, like doing
or like
that
a plenum box or something?
Yeah, kind of. I mean, not obviously not like a hose connected to a pot sitting in a trunk, but my thought is like most of these intake manifolds, you see the majority of the plenum area is kind of in between the runners. Like, is it still advantageous to have extra? If you could go outside
a couple more
of the
inches,
runner, would it still be an advantage? Because then you'd have a little bit more option from a packaging standpoint. It might look funny, but you could still get the volume that you're trying to get.
They call that a Kinsler. As a joke.
Well, so when you frame it that way, I'm going to say generally yes. If it's accessible volume, yeah, it will probably help you.
The major reason I'm asking because we're actually in the middle of designing 2 intake manifolds right now, and some of this stuff is like damn, like I wish we would have known some of this stuff earlier on.
No, man, I'm right there with you, Chris. I'm totally right there with you. That's why I was like messaging Blake Hughes offline. I'm like, man, you guys are working on intakes. You should be listening to this.
I've said that many times. I wish I knew this thing. Yeah.
I just messaged my business partner and told him he needs to sign in and listen to it because we were literally, before I left and got on the podcast, we were looking at the whole thing in SolidWorks and just kind of talking about it.
Yeah, there's a couple.
So that's one of the problems that we're running into right now is that, like, because of the space constraint, this one particular intake that we're building is designed to fit on 3 different vehicles, so it has to be compact in certain areas to fit all 3. And the plenum volume really isn't what we would like it to be. So I was wondering, like, if you could go outside of that area, if it would still help. So I guess you're saying it would.
Well, yeah, I mean, again, it depends on how it's executed. If it's kind of really far away and it doesn't really fill or enable filling the runners, it may not be. It may not help as much as if you could put it directly over the runners. But here's a tip I will say: if you can feed the plenum on the side and then that plenum feeds into the runners, that actually generally helps because as you're coming through the throttle, you need to slow the air down before it comes out over the runners. There's some manifolds, like, it's very tight. The throttle is directly over a runner and it's fairly tight and often kind of a sharp edge. So as you discharge into the plenum, it basically just shoots right over that runner. So you're going to tend to pile up air in the back. You're going to kind of starve the runners in the front. If you can feed into the side and kind of fan that plenum out over the runners so the air slows down before it gets to the bells, the entrance to the runner, that generally helps. You're going to get better air distribution across all of them. It will generally probably make more power doing that versus trying to feed it right into the plenum, right on top of a runner.
And when you're saying you need to slow down the air coming in, so like a lot of these so the transition between the throttle body and the actual plenum should be as abrupt as possible, right? Because that would give you the most reduction in airspeed as it enters. Because I've seen some where like the throttle body and there's like an inch thick flange on there that it has to go through before it gets into the plenum. So that if you were just go from the throttle blade and then it just basically opens directly up into the plenum, that would actually be better than having that extra length, I guess,
Well,
behind the blade.
I can say that when we did the Carbon TR, Caleb was losing sleep over the transition from our 125 millimeter throttle body to the plenum, trying to get the short side radius correct. That was like he put more effort into that than any other part of the manifold, if I remember.
Well, I was going to say, yeah, your question, it logically it makes sense, but it's actually the opposite. This is where physics come into. Basically, if you have think of your airflow coming in as sort of a jet stream of air. If you have a sharp edge discharge, it comes out, it will maintain that jet stream and kind of basically flow as a jet stream into the back. What we're trying to achieve coming out of the throttle as we enter into it is flow attachment. You want the flow to attach to the wall and basically diffuse into the plenum. You don't want it to jet stream into the plenum. At that point, when it does hit the back wall or hits the next thing, it's going to kind of tumble and turns into kind of a big jumbled mess. You're not controlling where the air is going to. You want to come out of the throttle and diffuse it. So it's the best description is a reverse bell mouth. You basically want to start to taper it out and bring it that taper tangentially into your plenum volume. And honestly, like a 1/2 inch radius, if that's all you have room for, do it. Make as big a radius so that it can diffuse into the plenum. The sharp edge is, I never say never, but the sharp edge is generally the wrong way to go. And you'll be surprised. There's a lot of intake manifolds out there made by people who really know what they're doing, but they still have sharp edge discharge into the plenum.
The sharp edge creates laminar flow, and that's what you're talking about right there.
Yeah.
So it's kind of like a megaphone on like an exhaust sort of kind of.
Well, this is something that Chad probably has a lot of input on too, because we're talking about slowing it into the plenum so that it can cause basically you're going to slow it down to create a higher pressure above the bells, but so that it can also make the turn. And it's the same thing that Chad's doing in a cylinder head. If I'm interpreting this correctly, what do you think, Chad?
Oh yeah, no, I agree. I mean, that's the big debate again on a smooth finish versus a burr finish, and I mean, I think if a guy really understood what you're doing to the port wall when you burr it, and actually were into velocity and into velocity gradients and into localized points, I think you'd see some stuff. Well, actually, I know you would. I mean, I'm starting to see even now cylinder heads that have a different step over from this beginning to the top of the apex, or they're using the step over to manipulate the velocity, which that's all you're doing when you're doing finish, But yeah, I mean, I totally agree with that. I mean, I've done, I call it hillbilly testing. I mean, a bottle of Dicam and some alcohol will do wonders. I just I hear exactly everything he's saying, and I guess to some degree, if it's wrong at the beginning, it's wrong at the end. You know what I mean? And I think a lot of times people, the whole concept of having things as smooth and as shiny as possible for the airspeed is just, we've got a boundary layer that we're dealing with. We've got things going on, and I mean, I call it total chaos. I mean, it's chaos in that port, and all we're trying to do is manage it. That's all we're trying to do. Caleb's telling you his ways he tries to handle it. with a single plane manifold, I try to handle it different with burr finish, and that's all we're doing. And I think a lot of the gains that are coming nowadays are from, let's face it, some of these engines out there, the cylinder heads have gotten better, but that's not where all the performance anymore is coming from. It's some of those things are peaked, so it's guys like Caleb that understand that, it's got to be right going in, or it's not going to finish right. But I put a lot of time in burr finish. I don't, people, I think in the beginning, people thought I just took a grinder and just made it look burr, but that's not my theory, and I actually had to put a disclaimer on my website, saying if you don't want a burr finish manifold, don't order one, and again, I've back-to-backed it. I've literally went to the racetrack on the same day and back-to-backed it. Same manifold, same car, 3 hours later. And I used to talk about it, and and I don't know if it's when people they don't understand, but then I love my engineers. Everybody's got to love their engineers, but if there isn't a paper on it, it's not valid. But my theory is my paper is if it goes faster down the racetrack, it worked. It may not work for everybody, but it worked that day. So, but it's all about the air. Caleb, he's dead right.
Another question that I kind of always wondered is, well, two things. Like I see a lot, like for instance, some of these N-Line 6 intake manifolds, it'll have a really wide entry and then it tapers as it gets more towards the rear, towards the back few cylinders. And I see that some people do it and some people don't. And I was kind of curious, what are your opinions and thoughts on, I understand like why they say it to do it, but does it really make that much of a difference?
So the plenum volume and shape, if you're in the ballpark, you're not going to make huge differences. It's when you start getting out of the ballpark that you start seeing issues. So the primary thing that I like to look at, if we get to that level of detail, in a plenum, like doing CFD, we will look for, and this is more important in dynamic because it looks different in the plenum than it does for steady state CFD, but we're looking for dead spots. If we've got dead spots, if we hem that dead spot out, it may help the overall dynamic flow of what we can get into each runner. That's getting pretty advanced, and so I think we have that sort of kind of shrinking taper shape on the our Carbon XR. Part of that is also packaging. Generally, like I was trying to bring the overall width down as we start going back towards brake boosters and other components. I didn't want it to be as large and as wide as it is at the throttles. At that point, I think I thought there was some advantage to the plenum. I don't know that it would be much different if we made that more like a constant shape. The other thing it got us is making it out of carbon is compound curvature is stiffer, so it helps the sidewall stiffness. I'd like to touch really quick on that throttle diffusion. It is very similar. Mark brought up the point like how it's discharging into the cylinder in the head, and they are similar, and there's certain things that we want to kind of have some similar features between the two. The difference in the manifold versus the cylinder is if we get the air to discharge into the cylinder, it's captured there. Versus the air in the manifold, we're trying to it's not captured, and we're trying to manage that chaos inside the manifold. The other thing is inside the chamber, we're getting into combustion science, and there's swirl and tumble, and there's turbulence that you want to induce that we don't want to induce inside the plenum. So there's similarities and differences. And Chad hit on something that I want to agree on, because surface finish, so many people want super shiny surface finish. We don't want a glass finish. I will admit some of our parts in certain areas, because of the tooling, like our carbon bells, they are a very high polished finish. But CNC ported runners and even our runners in our Carbon XR, it's not the tooled surface on the inside. It's a very it's a fairly smooth, but there's a texture to it. I think it's darn near close to the ideal surface. You don't want high gloss. High gloss is actually higher friction, so you're going to have a thicker boundary layer. If you can manage the texture right, it's kind of like a golf ball. You get a little bit of, I don't know if the term is correct, but micro turbulence, like at the surface, so that you have less friction and more flow in that.
And you can show this in CFD even?
Generally, CFD won't show that. We don't model the surface finish. You could go to a very, very detailed analysis that you could probably do that. We don't look at it, no.
So the other question I have that I'm surprised no one's brought up yet is, how does runner taper affect things, and when do you want to taper and when do you not want to taper? Why would you taper? Why wouldn't you taper? Because I see a lot of manifolds nowadays tapered runners. It's like for a while you didn't really see it, and now it's like everyone I see that's billet's got some kind of taper in the runner now.
So my opinion is taper is frequently manufacturing driven. How do you make that part? If it has to draw off of a tool, you have to have a line of draw and draft that induces taper naturally. We generally put taper, we look at taper more with respect to, so often our job starts at the head flange. So Chad has already done his job and we're trying to match the runner area, and we'll look at the taper in the runner and try to match we look at the area schedule and look at our area schedule in the runner to make sure that matches and is tangential or a fairly good best fit curve to the runner schedule in the head. The amount of taper, more taper, we find basically more taper tends to change the effective tune length of that runner. If it's a 10-inch runner with more taper, it's going to tune like a shorter runner, and a constant area runner will tune at a longer runner length or a lower RPM.
Can I stop and ask a dumb guy question? I'm sorry to interrupt. Just a quick question for the basics. Do I understand it right that when you say tuned, you mean we're trying to get it so that there's pressure waves arranged such that the high pressure is at the intake valve when it opens up? Is that am I understanding that right, or is that oversimplification?
No, that is good. But if you want to oversimplify it even more, where does the engine tune peak? Where's our peak torque? Is it at 4,000 RPM or 5,000 RPM? So a longer runner will tune at a lower RPM.
Got it.
As a generality, there's a lot of different variables, but that one usually, I think Mark, you talked about running a Hillborn like different lengths every inch and a whole bunch of different lengths. I'm assuming that basically your peak torque just went up or down the RPM as you change that length, almost linear to the length change.
Okay, so that was on a Hillborn. So we had a unlimited plenum, right? So each, we don't have cylinders sharing plenum volume with each other. But what was interesting is it changed where the large rises in the torque curve were as far as RPM goes. But in a 3,000 to 6,000 RPM pull, the average torque didn't change. All the runner length did from testing from a 12-inch ram tube down to a 7-inch ram tube, it changed where the torque was made, but the overall average didn't change.
Yeah, you're usually just shifting. You're shifting the peak. You're just twisting the torque curve back. You're kind of rotating it. It's especially with that kind of setup, that's about what you would expect. And it's going to be a lower peak RPM with the longer runner, higher peak RPM with the shorter runner.
And by the
way,
way,
with that peak with taper too.
Yeah, and for those listening, like at 3,000 or 3,500 RPM, from a 12-inch runner to a 7-inch runner, it was an 80 foot-pound difference on a 900 foot-pound motor.
How much peak horsepower or torque did you lose off of that?
It's not that it lost peak. The torque really stayed within a few foot-pounds peak. It's just where it peaked. And the thing is that the really long runner fell off really hard at higher RPM, so it didn't have the best shape, because it made huge torque from 3,000 to 4,500, and then it fell off. The average was still the same, but it wasn't a very ideal curve. And then the 11-inch did this, and the 10-inch did that, and the 9, and each inch that we removed from the ram tube made a different torque curve. I ended up using a 9-inch ram tube because it gave the best average.
So basically, it gave you a hump that moved from lower torque to higher, from lower RPM to higher RPM as you got shorter and shorter.
Exactly. Did I derail you, Caleb?
No, I think I didn't really have anything to add. You're spot on. I mean, I guess the one thing to add to that is that long runner, if you started to put some taper in it, you would then probably start to shift it up again, and you might be able to pick up a little bit more area under the curve. Depends on kind of some of the other tuning dynamics. But it's going to be generally hard to beat an ITB with no filter or no plenum around it. It's gonna act more linearly to your changes than other packages where you've got a plenum and filters and stuff like that.
Yeah, I know when we for parks we did an old school Hemi that was just basically a piece of cast when we started, and I mean they had to use an old OEM 390 block, but Scotty had so much weld in it to get it to work. But anyway, long story short, they had the manifold or the IR, because you can run alcohol individual runner, and the placement of the injectors was about 130 horsepower. Just on because the runner itself, you're only talking probably, I don't know, I'd have to ask Scott, but I bet you they weren't 3 inches long total. These things were like a 384, and he was turning it 10.8, 10.9. But the actual runner was only probably 3 inches. But the placement of the injector was super critical on that deal. In fact, I wouldn't have believed it if it wouldn't have been those guys telling me. How's that? But they fought it because they first put it on the dyno and it wasn't making any power, so they got out the tools and started making holes and moving that thing around, and bingo, they found it. So it goes back to what we're,
Well, I'm going to just throw out a theory, and I don't even know if I'm even half close, but they might have been mechanically moving the injector to catch, call it a wave tune, where they might have been able to do it electronically with timing and accomplish the same thing. But I'm only throwing that out there. I don't know.
Yeah, I don't know. I wasn't there either, but they, it's something that he always keeps bringing to my attention when we start talking about, what do you think? But yeah, it was pretty shocking. It was a lot of power.
So I guess I had another kind of question. I have a lot of questions, so just stop me if I get annoying.
Doing fine, guys.
I see you've got single throttle body intakes, you've got dual throttle body intakes, and you've got these like oval throttles that are, typically have a pretty high area and a smaller package. So have you seen many? Have you got to play with that and seen how those different configurations affect the overall performance of the intake? I see a lot of dual throttle bodies. It's like you have guys with like twin 90 millimeters versus one guy with a 125. Really, what, if you're not pulling a vacuum in the intake, do you really need a bigger throttle body? I guess is what I'm getting at.
Generally, I'd say no. You just need to make sure that you have enough area. And in my opinion, oval is only a means to get an area in a packaging space. But I want to share something. A GM design release engineer for throttle bodies. When we were working on the V16 in 2002, we were doing oval throttles because the design studio absolutely required it. It had to have oval throttles. It had to have a very specific look for the engine. We could package around. We could have packaged anything. And we were making these things, we were designing them and building one-offs. So getting the throttle right was pretty critical. We talked to this design release engineer, and he said, well, the first thing I want to tell you, above all else, I wouldn't touch an oval throttle body with a 10-foot pole. So the manufacturing tolerances to be able to get that thing to seal is exponentially more difficult. And I can tell you firsthand that we had very good machining capabilities. This was at K-Tech. We designed the parts, we machined the parts, and I can tell you from hand fitting them personally that he was right. Like getting the fit and getting a very tight seal at closed throttle is extremely difficult with ovals. So stay away from them if you can. Sometimes you can't, sometimes that's all you can do. But in general, you're looking at make sure that you don't have a vacuum in the manifold.
I just mainly don't like them because you can't find a heavy duty enough clamp to hold any kind of boost on the oval throttles.
Yeah. The only thing I can imagine is as you get into like individual applications, if you're packaging that you need that much, you need oval to get the area, or B, maybe when we talk about that flow attachment from the throttle into the plenum as it diffuses into the plenum, maybe you have some benefits that you can gain there. But in general, I've never personally had a requirement that I had to use an oval because I couldn't fit around. So I would say you can generally always use a round, and then at that point, you're looking at how much area. Make sure that you have ample area, that you're not getting close to the maximum flow through the throttle. The other thing I think a lot of people don't realize is if you think about the force from the vacuum, obviously big ratty race engines don't have as much vacuum, but still, if you got a 125 millimeter throttle and you look at how much vacuum there is and how much pressure is trying to push that, if you look at the area and the loads that you can see in that size of throttle, you better have a very good, very large, very high grade steel shaft to make sure that thing doesn't start flexing. And
I think
fairly
Scott
good
could
bearings
comment
as well.
on this from Tuning Pro Stock.
Yeah, do you see failures in throttles or issues there, Scott?
Well, when the Pro Stock cars first came out with the oval throttles, I think they were having all kinds of blade control.
They broke a lot of them.
Yeah, they were weird. They gave us all kinds of weird fits, and they did weird things.
Throttle also.
They would flex, and you changed idle behavior and drivability. You'd have to push on them, and then bam, they would slam open. They re-engineered them. They reworked them twice, I think. But we ended up with something that it's still an on-off situation. I'm not really happy with it. And it still
one of my biggest complaints about the oval throttle body is that transition from idle to just off throttle where it just cracks open, because now you've got, if you think about how the shape of a circle is when it opens, the amount of area that it opens up, the top and bottom, changes drastically when you change it to an oval. So you lose the fine tuning ability of that circle when you change it to an oval.
Yeah, you lose resolution in the tip in. And if you look at every production round throttle now, they all have machined progression. So you have a mechanical advantage for higher resolution as you tip the throttle in. You have better control over the area, the actual area opening of the throttle, so that you've got better drivability.
I think it's funny. I see these guys port those things out all the time. I'm like, you guys don't realize that is there for a reason. It's like,
and they're probably not going to pick, most of them, you're not going to really pick up power. If you do, you're giving up drivability for it.
Right, exactly.
Which some guys don't care, right? Depends on what you want.
I've had some where they're ported so big that you can't even get the car dial down far enough because there's there's just a big gap around the blade, and it's ridiculous.
where you can benefit is cleaning up the IAC passage that's in the front of some of those and making it rounded going in to allow the airflow to go through the IC better.
So the other half of that first question was, have you ever seen a situation where having two throttles, in a single plenum is advantageous other than just the pure area, or does it cause any issues at any point?
I can't say that I've seen any issues that weren't just directly related to too much area, and as the throttles open, you have too much air. We have a dual throttle cross ram manifold, and what that primarily did was enable the cross ram architecture without having to have a crossover with a single throttle. That would have added to complexity in the overall packaging. We had figured that most people would only need 75. Actually, most people would only need 70 millimeter throttle bodies for that dual 70s. But between having trouble finding decent throttles and most of those throttles having straight bores, we ended up going to dual GM90 or the 87 millimeter truck, because the drive-by-wire with the mechanical lead-in, like the machined lead-in, between the drive-by-wire and that lead-in, dual 90s were easier to tune and easier to run than dual 70 or 75 mechanical throttles. So it definitely, I will say, with ours, it complicates the tuning, and it's not so much because of throttle area, it's because of dual drive-by-wire. Because we've had some customers who take one drive-by-wire, they modify it to be a mechanical slave, they attach it to the single drive-by-wire master, and when they're running a single drive-by-wire with any controller that will do drive-by-wire, they can tune it and get it to idle and drive so much easier. They've got to play with it because the amount of air at each idle position, has increased, has effectively doubled. But that's way easier to calibrate. I'm not a calibrator. I think it's funny that I'm on this show. But they find it much easier to calibrate if it's a single drive-by-wire, and just going to dual drive-by-wire, even though it's the same exact mechanical flow, it's a much more complex system. And that probably gets more into electronics and algorithms than it is the actual throttles themselves. So overall, I think going higher would be, I think you're just getting into how much area do you have when you tip into the throttle that you start to have problems.
Did you take notes, Chris?
Yeah. I've done a lot of dual drive-by-wire stuff, but I usually have separate control for both throttles.
Right.
I never used one of those. I've seen like videos of those things. I think a bigger problem is that the secondary throttle always lags behind the primary a little bit in all the videos I've seen. And I think that could play a big part in making that difficult as well. But I've done a lot of like cars with dual throttles, like GTRs and Lambos, and I've done some big V8s with dual, like the 90 millimeters.
And each throttle had its own H bridge in the ECU. Yeah.
Right. When you have control of each throttle independently, it makes a huge difference in how well you can get it to behave. So, from an intake manifold design standpoint, there's other than maybe some drivability off idle, there's really no airflow anomalies that could that would be from having 2 points of entry. I guess is kind of what I was getting at.
No, I don't think so. In fact, you may be able to take advantage of it and first potentially slow the air down more as it's coming into the plenum. You might be able to better orient where does the air come into the plenum. I think I don't think I said it earlier. If you can feed off to the side of the plenum instead of directly over the runner, that's generally advantageous. So if you can feed into the plenum, I can't think of the exact applications, but there's some Audi manifolds where they've got dual throttles, and even some like the Ferraris where they they feed off to the side and it kind of tapers into the side of the plenum, you're allowing the air to slow down. If you've got 2 entries, you're flowing half the amount of air on each side, and it's just got more time and more volume to be able to slow down and be able to stay attached to the plenum and flow around the rest of the plenum. It's flowing into chaos, but you give it the best chance you can by keeping it attached as it comes into the plenum.
So the ideal situation would be basically to have still air sitting in the plenum when that cylinder goes to pull air in. That's kind of what you're trying to achieve.
Yeah, there's no such thing, but
right. But I mean, yeah, that's like trying to run a zero ET. It's always the goal, but you'll never get there, but you get as close as you can, right?
Yeah, and I think that's probably what like an ITB throttle is closest to achieving. Right, you've got time for the air to stabilize back to ambient pressure around the entrance of the throttle.
So when you're trying to calculate runner length, how much does the port length actually play into that? I mean, I guess across a certain engine platform, the length would be very similar, but
yeah, it's critical. You can't calculate without the port length in the head.
Because you're really calculating from the valve, right?
Yeah, from the bell mouth to the valve, and we always calculate to the theoretical sharp of the entrance. We calculate a length and then we add the bell mouth on. We don't make an adjustment. Overall, I don't think it really matters where you calculate to, as long as you're consistent, so that as you learn more, you understand what you're seeing in relation to what you've designed.
That makes a whole lot of sense.
I guess this is kind of a dumb question just for me. Obviously, there's a bunch of turns and this and that. Are you using the average of the length, or are you using the top side of the runner, or the bottom side of the runner?
Center line, we approximate based on the center line. Okay. The center line distance. If you take the top and bottom, like a front view, you take top and bottom and split that, and then same from a top view. So if you're taking an existing, like in CAD, take an existing head port and runner port, you can either convert some of those entities and create center lines. You can create sketches to find the exact center, or sometimes you just have to ballpark it. You do a best fit, eyeball it, but you basically calculate the center line distance through that 3D travel.
I usually use a seat ring, or the actual seat, like the 45, to make it consistent, like you said. That way you always know to go to the same place. I usually use solder too. It makes it a lot easier. Lay solder on the floor, lay solder on the roof, and then just lay it on a flat table and draw a line and then measure it that way. Divide it by 2.
And then you just average the 2. Yeah.
Yeah.
Yeah. If you're physically measuring, just measure the physical parts and average to get your center line.
Yeah. Then say like on a manifold, I'll just grab like the center of the divider and just pull the tape along one wall. Which they're just crude measurements anyway, but that because you can spend a whole lot of time measuring on things and then you can never come up with the same thing twice.
Yeah,
drive you crazy.
Yeah. So I understood what you said about the taper changing the effective runner length. So how does it affect the velocity? Because like I see a lot of people, just reading around saying that the velocity that's their main goal of the taper is to increase velocity going through the runner. Is that a side effect of it, or is that just kind of is that the whole point of doing it? I mean, where does that come into play, or does it even come into play?
Well, you're accelerating going back to your question about if it was theoretically still air, you're taking still air and accelerating to all the way through to the seat. So the taper, you're accelerating that air, so more taper gives you more time to accelerate it, but ultimately your peak acceleration is going to be down at your pinch point. what we're looking for in terms of velocity is a nice gradient as it's accelerating to that peak velocity. The taper plays a part in the tuned length. Sometimes it plays a part in the manufacturing. Can you manufacture it without taper? We're manufacturing some bell mouths out of carbon right now that you can't pull that carbon bell off the tool without taper, without doing extra work, like heating up and then freezing the tool so that the tool shrinks and the carbon can pop off, which just adds complexity to the manufacturing. It's possible, but
so you're saying that the taper is more commonly just a side effect of manufacturing more so than a tuning tool for wave tuning?
No. That's one of the factors. I would say taper is most often part of the tuning and the overall design.
Okay.
I'll say that some of my empirical evidence says, like the LS7, just to give you examples, the LS7 really likes taper, and the LS3, the best I can tell at this point, I think it wants constant area, and I have not been able to determine why. They're very similar engines.
Caleb, have you ever found that, let's say, like you're working with a cylinder head that has the minimum at the pinch? Have you ever found through data that would be where the runner length would start? In other words, what I'm saying is if the manifold physically had, say, 6 inches, but the actual minimum was 3 inches in from the flange of the head, have you ever found that the manifold and the cylinder head and the induction is working like a 9-inch long induction? Follow what I'm saying?
Yeah, I follow you. I don't think I have, because I think the effective from that pinch point to the seat is not a huge difference, but then once you get into the chamber, it's a big volume difference. So I can't think of any that I have seen that does that, but I will say I've seen it on the opposite end, where there's a feature that you can tell the design intent was one length. Let's call it 9.5 inches. Anyone that's familiar with some of the OE CAD that you can get through SEMA, if you dig around, you can probably find this, or some people might already know, but there's one specific production manifold that has features that you can tell. When you look at it deeper, you go, okay, they were trying to make the bell right here. Let's call it at a 9-inch length. But then because of packaging, the plenum volume kind of curves down to stay within like the packaging constraints. The effective length, and it's not a very good effective length though, is more like 11.5 inches because of that curve. The plenum curves down, and it's got like a 90-degree. It's effectively a 90-degree entrance into the runner, so it's got to make a hard 90 and then go through the runner. So you actually pinch it down as it's making that turn, so you've already lost some potential flow because of the 90-degree turn, but also it's tuning at this 11+ inch length versus the 9-inch length. Right. So the intent did not. When you start flowing CFD, you see it pinching down. You go, realize they totally messed up the bell on this thing. You just fix that, and you're going to pick up a lot of power. That's where you see some manifolds. It's pretty easy to pick up power because there was. I don't know that it's a mistake, but based on the constraints and what they were working with, they ended up with this certain design, and you fix this little detail, and you can pick up really good power. The LS3 is again a very good example where they got it right, and it's hard to make power. So it's the reverse of what you just asked. The tune length is different than what the design was, but it's on the bell side versus the pinch point side. I don't think I've seen any where it tunes to the pinch.
Gotcha.
I kind of want to take a step back. You mentioned that you were working on basically the air going from a dead stop to accelerating. Do you also worry about the opposite when the air's got to go from accelerating to a dead stop, basically, i.e. reversion?
Yeah, that's his name is escaping me. There's a very prominent professor, I think it's Gordon Blair, has a really interesting article about taper, and he's a very big fan of taper. I am generally a fan of taper, but I've seen instances where it doesn't work. Taper tends to help reduce reversion out of the runner. So a larger bell with more taper tends to help lessen reversion. I also talked to another rather experienced engine designer who worked in Formula One for 25 years. And we talked about taper, and I proposed the idea that, well, if you're looking at the center line length, but then you put a bunch of taper in it, is it tuning to the center line length, or is it tuning to that effectively longer length that it takes to go through the taper out to the edge of the bell? And his answer was that he thought it kind of did both. And I kind of got a chuckle, but he said, "How do it know?" How does the air know which one to do? That kind of gets into where we start looking at the 3D acoustic tuning, because we see what the actual acoustic resonance is inside of it. So that taper, it's a little bit like runner length. You can play around with it, and what you're generally doing is just sweeping the tune point up or down the curve. So if you're not hitting your effective tuned length that you want, you can play with, the tuning, the peak tuning RPM, you can play with length or taper to try to shift it a little bit. Length is usually easier to directly correlate some calculations to how it's going to affect RPM. Taper, I find, is not as direct.
Some of the guys are asking about some of the newer manifolds where they put the throttle body and the plenum underneath the runners and then wrap it up around.
Bottom feed, yeah. Seems like a lot of turns.
What are your thoughts on that, Caleb?
Talking like the Hemis and the LS and the Coyote, all the current like modern.
They're talking more along some of the sheet metal intakes that are out there where they might have a tube underneath the main plenum floor and then slots that feed up, or maybe a curve like 180 on the backside that feeds into an upper plenum to try and package everything for a lower hood height.
Yeah, I think that two things. It's predominantly trying to get a lower hood height. We have a tunnel ram style that we designed, we never manufactured, that was a bottom feed, and with raised bells. And the idea was that we gave us more time to slow the air down to feed the plenum, so that the air would come in and go up. The biggest reason for doing it is that we could get the same runner length in about a 5-inch lower total packaging volume.
Does that curve make a difference on the runner length, i.e., that 180-degree curve adds, like the equivalent of an inch of runner length? Does it change anything?
Depends on how. I don't know that I could say it changes the effective tune length, but that's where you start to play with taper. If you've got some tighter turns, you might add a little bit more taper so that you've got your area schedule increases as you make the turn. Think of it as like a cobra neck on air intake, where when they're turning, it gets wider. You're just trying to use the area schedule to overcome basically packaging issues in the flow path. So if you're making a tighter turn, you need to increase the area schedule so that you don't restrict and speed the velocity goes too fast through the turn, then slows down again after it makes the turn. Trying to maintain a nice acceleration gradient of the air.
So basically, you're trying to avoid big changes in speeding up and slowing down because of the turn.
Yeah, you'd like ideally up to that pinch point, or up to the point where you have a constant velocity is probably a better way to put it. You'd like to have a constant acceleration of the air to that pinch point, or an increasing acceleration if there's some curvature.
Okay, cool.
Very cool stuff.
Did we wear him out? Only been almost 2 hours.
He's
Yeah,
gonna be
getting
like,
close.
man, you guys killed me here.
Yeah. I mean, Caleb, what else do you want to talk about to cover, man? I mean, you can cover the manufacturing end. It's kind of interesting. There was some interesting stuff talking about there earlier before we started.
I don't think he got to talk about his V16 very much.
Yeah, that too. So what we got? Let's take that last 10 minutes and make it have. I mean, whatever you want to talk about, go for it. But we've been bugging you too much about intake manifolds and design.
I love this stuff. I when we're deep in a project, I literally design this stuff in my sleep. I will be thinking about this stuff. I usually forget it by the morning. Sometimes so I can't quite say like it came to me in a dream, but we do a lot of intake manifolds. It is the predominant focus of what we design and manufacture, especially on the manufacturing side. We have designed complete engines, and some of the funnest projects I've ever worked on was the Modus V4 engine. The V16, it's kind of there's two V16s. I should clarify. We at K-Tech, we did one for GM for their concept car for the Cadillac 16. That engine, when they came in for a quote, they had prepared us that they would accept quotes where two blocks were welded together, or potentially even only running the front block. So it could be a V8, but it had to have the V16 size and overall architecture. But
interesting.
We knew when that came. Well, they wanted it to be a running V16, but
sure, yeah.
Overall, they're trying to balance constraints of this is a concept car. So we knew we wanted the job. We would not weld blocks together. We wanted a full cast V16 block, and it had to be running. And the target was 1,000 horsepower. So we knew we got to hit 1,000 horsepower, which back then in 2002 was astronomical. Even the 500 horsepower, out of a V8, even then was very, very pretty big numbers. So, so that project from winning the job, from the kickoff meeting to first firing on the dyno was 7 months.
Jeez.
It was a complete bespoke design block, lower bed pan, literally all new heads. It was all borrowing off the LS6 architecture at that point because it was the state of the art. So they were 8-cylinder heads. They were all cast in Germany by Becker. We machined them in-house, assembled one running engine, one display engine. So that was 7 months. Then it was another probably a month and a half for little details before it was unveiled. They were gluing upholstery into the back seat of the concept car behind the curtain like minutes before they unveiled it. We were in the back with them. Luckily, our part was all done because the engine was in the car. It was already driving on its own power.
We have a couple of guys that do SEMA project cars or stuff like that, and it's not dissimilar. I know Brad, I don't know if he's on here listening, but he's like, I had to do wire harnesses while they were still putting upholstery in. It's a bunch of bullshit. But yeah, carry on.
Oh yeah, same exact thing. But this is General Motors,
right?
Unveiling to the world. It was quite an interesting thing. And so the 16 that you're talking about now is it's a sister company to Performance Design, 16 Power. And the idea is to take that concept that was kind of the feasibility was done, right? They proved out, it wasn't as big a challenge as we expected. It certainly was a challenge, but it really proved the feasibility. And we thought from the beginning, back in early 2000s, it would be a great marine engine, but nothing ever came of it. We built one more running engine that they put in a Yukon, and it's still running around, I believe. But 16 Power decided it was time to commercialize the concept for marine performance. And we did a couple of very unique things. Number one, we had to redesign it from start because the design and the tooling was GM's. They owned it from that project. I couldn't take any sort of risk that there'd be any sort of conflict there. So we redesigned it, but that gave us an opportunity to take a look at how do we take this from the feasibility concept
Sure.
into
it's another iteration opportunity, right? So yeah.
You get to do it
It's
a second
awesome.
time.
Yeah.
And to actually take into account marine duty cycle versus a concept car that only has to idle into the show.
Right.
So, it is a single block, but we took the front 8 cylinders and the rear 8 cylinders and we split it. We put 1 inch in between them. That allows us to use off-the-shelf heads. The real key thing there was that we didn't want to limit ourselves to tooling a head when we could use anything off the shelf, any production, OE production, racing, performance, any new versions. We could use LT heads, LS heads. It gives us a huge variety of ingredients to basically kind of to create different recipes. But the key was doing the block. It's a fully tooled block. It uses a low pressure casting process, which was developed by Cosworth originally, but this under a very controlled manner puts the molten aluminum into the mold from the bottom and feeds it up, so you don't get the tumble and swirl as it from a gravity fill.
Oh yeah.
So it's a much more pure, and you get much higher material properties because it's a more controlled process, less porosity, far better casting integrity. So that's actually cast in Roseville, Michigan, kind of right down the road from us. So it's a complete tooled block, complete tooled lower main housing. All the main caps are all tied together in an integrated lower bed pan. It's got the standard is 6-stage dry sump, 1 stage scavenge for each 2 bays.
Oh, cool. Yeah.
So we've got 8 bays, but then we've got one that's dedicated. That spot where we split the crank, we've got a cavity that comes from the valley and pulls oil from all the heads. The valley is kind of angled, so it all comes into the central location and feeds down the center of the block, so it doesn't all go out over the crankshaft. There are still some drain backs from the head, but the predominant drain back from the whole upper end comes down through this central valley, and that has a dedicated scavenge pump.
Is that for windage concerns? I know it's a dumb question, but
windage concerns, oil control. We're also thinking about like the G loads in a boat. It goes airborne.
Yep.
Off the wave, and trying to really manage our oil. We're going to make between starting like at 900 horsepower naturally aspirated, 1200 horsepower, then 1400 naturally aspirated. Then the next is boosted 1650 horsepower, and then 2000 horsepower. It could obviously go up. We've all seen some other V16s that are making really, really big numbers with really, really big turbos. We can do that, but that boat with that kind of power and that torque curve, it'd be difficult to get these 52-foot boats on plane. So we need a lot more torque at lower RPM.
Yeah, you got to get the boat up on plane before you can take advantage. And I mean, some of these guys are geared with one gear, like Todd Goodwin was saying, that they got a prop that's set up for 200 miles per hour, 190 miles per hour. That you also have to have a power curve that'll spin that thing and to get it at low RPMs to get it up on plane.
Yeah, so that was really the driver behind all the decisions that went into the design, was to make sure that we hit marine duty cycles and operating parameters so that we can get the boat on plane. It's about the same, marinized, it's about the same weight as the iron block V8 big blocks that is kind of like the
standard right now.
Yeah, it's the incumbent. And the other real thing, like we started looking at really why would you do this? If you start looking at a V8 that's supercharged and is really extreme valve trained to try to make these power numbers, they're making 200 horsepower per cylinder.
Right.
Just break it down to a simple, stress on the components, 200 horsepower, extremely aggressive valve train. Then you start to say, all right, let's split it over double the number of cylinders. Now all of a sudden you can make the same power at half the power density. which normally we're all going for high power density, right?
Yeah, but it's easier on everything to be able to do it that way, right? Yeah.
Makes it easier on everything. And if you want to go take that risk in terms of the durability, double your power density again, and you've got much greater potential performance on the top end with, a similar reliability to what they're doing now.
Sure.
So we really wanted it to be very reliable, but still make extremely good power.
Is it targeted for race type offshore boats or pleasure as well as high performance, or who's the target audience?
Pleasure poker run is probably the ideal.
Got it.
It fits in most 36-foot boats.
Got it.
Up to, obviously they're making 52 plus foot boats now. V-hulls, catamarans. Most of them have 2 engines, some have 3.
Right.
So it's really, pleasure all the way up to full racing programs, unlimited racing.
Got it.
What we think the real advantage is the reliability that we can obtain, the performance levels that they're looking for. But then if you look at a 52-foot boat that fits 6 people, right?
Right.
A lot of this is a more of a statement. Why does someone buy a Rolex versus a Timex?
Sure, that's the most polite way I've ever heard it put.
Yeah.
But yeah, carry on.
Yeah. So
there's a reason they measure it in feet. Yeah.
Yeah. So to put 32 pistons in it versus 16 total, there's a little bit of a
does the crankshaft have to be incredibly stronger since it's so much longer? I mean, is there anything? I'm really curious about crankshaft design and twist and things like that over that great length.
Yeah, so it's something that initially we were really scared about when we were doing the first one. You think, oh my gosh, we're going to make so much power and it's this long crank. But there's one key thing we've got going for us. It's firing every 45 degrees.
Right.
So
the pressure pulses are much better spread. Yeah.
So the instantaneous torque spike is actually much lower.
Much less angular velocity difference too. Yeah.
So you end up getting a very smooth, the torsionals are very smooth. They're actually within OE production passenger vehicle specifications. Like they're on the high end, but they're within like the normal specifications for a regular passenger engine. Now we are making a lot of power, so we do have it sized their big block mains, but we actually package protected to go up to a Duramax diesel main if we need to.
Got it.
So it's a larger main. Under the boosted application, we would actually shrink the stroke so that we get more overlap between the rod and the main. That's the main thing for crank strength is overlap for the between the journals and the material that you use. So these are all billet, very, very high quality material, as well as very specific attention to detail on the rod journal sizing. It's a 2-100 standard LS rod journal, but the larger main gives us more overlap between the journals.
Understood. That is cool. Now, what about engine management? Do you know anything about the engine management? What system are they using? Any details you have there on that side?
So right now it is currently slated to go to production with an OBR controller. They've done some custom software to be able to give us the management we need. It's overall perhaps a little bit more expensive than we would have liked, but having 16 injectors that we'd like to control sequentially.
16 coil drivers, I'm sure too. Yeah.
Well, I was just going to say I have to double check. We might still be batch firing the coils. I don't recall on that. I know that they're working on that. So I'm more the mechanical guy than the electrical
understand.
guy.
Yeah. What type of RPM range does this run?
We ran it up to 7,000.
Wow.
Right now we look at it as basically an LS engine. Anything that you would run LS.
Got it.
6600 is kind of like a really key peak power point for most of these boats.
Right. Okay. Awesome. Guys, you got any more questions for him before we wrap it up? Anyone else?
I got something to add here. I'll scan it for you tomorrow. What's your name again, Scott? I have yeah. I was looking through I got a book. It's my theory book.
To you.
it's my theory book, and there's probably 150 pages in it. But one of the pages that I have is the old Helmholtz runner effect. The math is from late 1800s, early 1900s. But it lays out all the math for you. Some of the things that it takes into consideration, like speed of sound and the displacement of the engine, the inlet size, the cross section of the runner, and it figures a formula for you. It tells you how much taper it should have and how much runner length it should have. Now, like I said, what I find interesting about it is it's 100 years old, but yet one thing that never changes in this game is math and physics.
Right.
You follow me? So
Physics, yeah.
I'll scan it, and you can post it up, and somebody might get a kick out of it. You might see something on it that might interest you. But it's I like stuff like this.
We'll
like
put
I said,
it up
that's
for
my
sure.
whole,
Yep.
Yeah, my whole folder's full of stuff like this. Just stuff I found online or stuff somebody sent me, and I copy it, and when I'm bored, I look at it.
Caleb, when you get a chance tomorrow, get back with me on what you else would like to add, because I can add it to the video stream before I post the stuff up tomorrow. But yeah, that's good. Both you guys.
You'll have to tell me where to find the video stream too.
Oh, no worries. It's all over. We got it on YouTube. You'll be able to watch the Facebook, but I'll put it up on the YouTube stream. Is probably the best place to put it and park it for links so they can watch the actual video. Cool. All right, man. Thank you, and can't thank you enough, both you guys, Chad, Caleb. And Joe, if he's still on, I think he's still conferenced in here. We didn't get to talk much about manufacturing, but you guys are welcome to come back anytime you like, for sure.
Cool.
So
maybe next time we'll talk about actually manufacturing.
I would like to, honestly.
Really was hoping to have Joe step in.
Let's do it next Wednesday.
Well, I think
I'm
that was the issue. That was the issue with the 180 degree manifold. Was it was going to be almost not impossible, but a lot of work,
difficult to make or to produce, I guess.
Yes, very difficult.
Got it. Now let's try it for Wednesday. If Joe's open, if we can talk Wednesday, and if not, we'll do it whatever Wednesday you can after that point. I know we got holidays coming up here, but man, I appreciate all you guys sitting in here and helping us out. This was a good show. All right. Well, go ahead, Mark.
I would like to wish, I just want to wish everybody listening a Merry Christmas. And if you don't celebrate Christmas, if it's Happy Hanukkah or whatever holiday you do, I'm Christmas. So
Mark's
Merry
attempt
Christmas,
at political correctness. Yeah, happy holidays.
I tried
man.
and I failed.
No, you did all right. It's fine. It's fine. Just everybody have a good time, chill out with your family, and hang out and do your thing and eat and get fat like we're gonna do. But go listen to RealTuners.
And if you don't think Die Hard is a Christmas movie, you're
There's
wrong.
something wrong with you. Exactly. We all love Die Hard.
That's funny.
Yeah. All right, cool. Well, I'm going to let you guys stay on the chat, and Caleb, I'm going to let you and Joe go here, but and I'll do my little housekeeping outro stuff. Let's talk about getting on next week and talk about part 2 of this, because we got more to cover, I think. I'd like to talk about the manufacturing of the plastics and the composites stuff. Like the composite manufacturing really interests me. I see a lot of billet, I see a lot of fabricated stuff, but really, it was interesting to look at the carbon TR manifold I got to work with and see how it was made. I had a lot of questions about that, so we'll follow up with that. But thanks, you guys. Appreciate it.
Love to.
Okay, wonderful. We'll talk to you then.
Thanks for having us.
All right, take care, guys. That was outstanding. These shows are getting better, but I just feel dumber and dumber as time goes on. But anyway. All right, guys. Well, once again, thanks to my panelists. Thanks to Chad Speier from Speier Racing Heads. Thank you, Caleb and Joe from Performance Design. That was outstanding. I think we're going to follow up with them more. Let's see here. So we have classes coming up. I advertised those at the beginning of the podcast, but go to RealTuners.com. We're starting to set up a lot of dates. I've got like 8 dates up there right now for classes coming up. All over the country, and I'm going to try and do 20 or more classes this year, so we'll try to come to a city near you. If you are a shop owner and you think you can get 12, 16, 18 people together to do a weekend class, get in touch with me, Scott@RealTuners.com, or you can find me all over Facebook. But otherwise, if you're interested, let me know. We're setting up dates now.
Hey, Scott?
Yes.
I'm going to crash your KP Racing date since it's like 1 block down the road from me.
That's good, man. That's good. No, you're welcome to come right in. So we'll have Chris Delgado at that class. Now everybody's going to show up. That's outstanding. So yeah, I know. I want to have it at your place, Chris, but you guys have dyno ready yet. So we'll do the next one there in a couple months later.
Yeah, Joe and those guys are good over there, so I'll come by and hang out.
Outstanding. Yeah, good. They came highly recommended by all you guys. So, okay, cool. Well, let's see what else. Check out, okay, so the webinars, we've got a bunch of webinars online. I'm going to start doing more of those again here soon. We've had some new requests for some info, things like guys want to talk about how to build a timing table. Everybody's really worried about ignition. That's a good thing to be concerned about. So might get Chris to join me on that one. But we'll look for one of those in the next couple of weeks. But anyway, if you go to RealTuners.com, you can check out the webinars that we have, the pre-recorded ones. You can stream those. And they're pretty cheap. They're like $15 and $20. They're usually 2 hours or more long, and they're instructional, and they were interactive. But it's always best to hit the live ones. We'll post on Facebook about that. Follow us at RealTuners LLC on Facebook. That's our business page. I put all the info up there. If you like what you hear, feel free to make a donation to keep RealTuners Radio on the air. If you don't want to come to a class or do a webinar, help us keep this show sponsor free, except when AT&T likes to burst in the middle of my phone call. I didn't quite understand what happened there. But anyway, yeah, so you can go to RealTuners.com and click on RealTuners Radio. There's a donate button down at the bottom. That always helps. We appreciate the guys that are making the donations. Very cool. Check out the archive of podcasts. All these are maintained on RealTuners.com under RealTuners Radio, but you can find them on your podcast providers like iTunes, Stitcher, Google Play, and again on our website, RealTuners.com. So that being said, thanks everyone for listening in. We will talk to you after Christmas. Everybody have a nice holiday, and we will get back together in 1 week. Take care, everybody.